Today we're going to be talking about help for related rates, and I'm going to combine all three homeworks into the same video because the process is the same for each homework. Let's make sure we understand the process for related rates. The first thing we're going to do is read the problem. And what we want to be looking for as we read the problem is we want to look for any constants, any variables, and any rates. Okay. These are three different things, and we want to make sure we have a good sense of what in the problem, and have a good idea of what's going on in the problem. For a lot of kids, this is the hardest part, is understanding what's going on in the problem. Second, we're going to draw a picture and label those same three things: any constants, variables, and rates. Third, we need to have an equation that relates the variables we have rates for. So the equation is going to have variables in it, not rates, because we're going to eventually do the derivative and get the rates out of them. Fourth, we want to make sure that that equation has only the variables we have rates for and not any others. We'll sometimes have to do this and sometimes not. So sometimes we need to substitute before doing the derivative. 5, we're going to do the derivative with respect to time because that'll tell us how much our variables are changing over time. It'll be, for instance, the change in the height over time. And then 6, we're going to substitute and solve. Okay, let's see how this looks. In homework 2.4, let's read this first problem. It says a tugboat moves a ship up the dock. So, okay, let's make sure we understand this. So there's this tugboat, and it's moving this must be the ship, it's moving the ship up the dock. Here's the dock. By pushing its stern, here's the stern, it's pushing the stern at a rate of 3 meters per second as shown in the figure. Okay, so this tugboat is pushing this 3 meters per second. You want to have a good sense in your head that this is a rate. Meters per second is a rate. That's the first thing. The ship is 200 meters long. That's the length of this ship. So this ship, this distance from here to here is 200. That is a constant that will not be changing. No matter how far that tugboat pushes it, the ship will always be 200 meters long. The bow remains in contact with the dock, so that's right here. This is remaining in contact with the dock, and its stern remains in contact with the pier. So basically we've got this boat that's sliding along the pier. Very soon the boat will look something like this, right? So the tugboat is pushing it down and it's moving along the dock. Okay. At what rate is the bow moving along the dock when the stern is 120 meters from the dock? Okay. This is the rate it's looking for. The rate the bow is moving along the dock. So the rate that this is moving along the dock, how fast is this moving? So we need some variables here. The variables in this problem are the distance between the bow and the pier. This distance is changing. I'm going to call it x because it's a horizontal distance. Also, the distance between the stern and the dock are changing. This distance right here is changing. We can see it's changing as the tugboat pushes down. I'm going to call that y. And so they're asking how fast the bow is moving. That's asking for dx dt. So it wants to know what is dx dt. This 3 meters per second is how the stern is moving. And how fast the stern is moving is going to be changing y. So that 3 meters per second is going to be involved with dy dt. The other rate, these are the two rates. The rate it gives us is dy dt, and because y is going to be decreasing, dy dt is negative 3 meters per second. So these are our two rates. We've got two variables and one constant. Now, it said the ship is 200 meters long. It also said the stern is 120 meters from the dock. That is not a constant. That's a value of this variable that's changing. So this distance is changing, and we want to know what is the rate at the moment when this distance is going to be 120. But this is changing. Okay? So when we set up our equation, the variable y needs to be in it, not the constant. So we need a relationship between x and y. And because we have a right triangle here, we can use a Pythagorean relationship. X squared plus y squared equals 200 squared. So that's 40,000, but we can leave it as 200 squared. We will not plug in 120 for y right now, because if we did that, we'd be calling 120 a constant when really it's a variable. Next, what we're going to do is, to get dx dt and dy dt, we do the derivative of both sides of the equation with respect to time. The derivative of x squared with respect to time is 2x times, by the chain rule, dx dt. The derivative of y squared with respect to time is 2y times the derivative of y, which is dy dt, equals the derivative of this with respect to time. We could try to do the power rule, but this is a constant. 200 squared is just a number. That number is not changing with respect to time. The derivative is 0. Now we need to plug in. The thing we're looking for is dx dt, so we don't need to plug that in. But we do need to plug in for x, for y, and dy dt. Now, we want to know what is this rate at the moment when y is 120. We can now plug it in after we've done the derivative. This is okay now. dy dt, we have here is negative 3 meters per second. We do not have x, but we can use the Pythagorean theorem to solve it. We can do x squared plus y squared equals 200 squared. We've got x squared plus, when y is 120, this will equal 200 squared. And solving for x, I know this is a 3, 4, 5 triangle, which is how I can do this in my head, but x squared is, I don't know, whatever 160 squared is. You just do 200 squared minus 120 squared. I don't have a calculator in front of me. X is going to end up equaling 160 when we do the square root of 200 squared minus 160 squared, or 120 squared. Okay, it's going to be 160. So we plug that in. 2 times 160 is 320 dx dt. 2 times 120 times negative 3 is negative 720. That's equal to 0. So we just move this to the other side, and we get dx dt equals 720. To get dx dt by itself, we need to divide by 320. And this doesn't simplify all the way, but it does simplify a little bit. Let's see, the zeros cancel out. We can divide by 8. So we get 9 over 4. And the units here will be, it's the rate that x is changing. X is increasing in meters per second, because those were the units for this length. That will be the same units for this length. Okay. Let's look at the next homework. That's the only problem I'm going to do from homework 2.4. In homework 2.5, we were dealing with geometrical related rates, but the idea is the same here. The idea is, and I'll zoom in a little bit here. I'm going to do number 4, which some people seem to have some trouble with. It says, at a sand and gravel plant, sand is falling off of a conveyor and onto a conical shape pile at a rate of 10 cubic feet per minute. This cubic feet per minute tells you it's a rate because it's per minute, and it's volume because it's feet cubed. So this is going to be a rate, and it's going to be dv dt. It's the change in volume over time. We can tell the volume because of the feet cubed, and that it's a rate because of the per minute. The diameter of the base of the cone is approximately 3 times the altitude. The diameter is 3 times the altitude. Okay. At what rate is the height of the pile changing when it is 15 feet high? Okay. So let's draw a picture of what we got here. There's a cone-shaped pile being formed, and we have a few things happening. More and more sand is falling onto this pile, so the pile is getting higher. So I'm going to call that H. By the way, H and A are the same thing. I'm going to rewrite this as D equals 3H. I just prefer height to altitude. But if you wanted to use A's, that's fine. This height is changing. Also, the cone's getting bigger, so this radius and diameter are also changing. So I need a relationship. It's asking at what rate is the height of the pile changing. The rate it's looking for is how much the height of the pile is changing. That's dH dt. That's the same as the altitude of the pile. So we have one rate that it gives us, one rate that it asks for, so we need a relationship between V and H. So you should know that the volume of a cone, volume equals 1/3 pi r squared H. Okay, when we look at this equation, V is the volume and we know dV dt, so we're set there. 1/3 pi, all of this is a constant. Pi is just a number. 1/3 of pi is about 1. R is a variable and H is a variable. We have dH dt, but we do not have dr dt. So before we take this derivative, we need to substitute for r. We need to get rid of this r, and we can only have the things we have rates for. The reason is if we do the derivative right now, we would do the product rule, and we would end up with, when we do the derivative of the first part, we would end up with a dr dt. And we don't have dr dt. So we need to get rid of r to make it only variables that we have rates for. So it doesn't mention anything about r, but it does say about the diameter. The diameter is 3 times the height, and we know the relationship between the diameter and the radius. Diameter is 2 times the radius, and so we can put in 2 times the radius for diameter here. So 2r equals 3h, and we can solve for r by dividing by 2. R is 3/2 times the height, or 3/2h, either way. So what we're going to do is we're going to plug in where it says r squared, we're going to put in what r is equal to. 1/3 pi, that's our constant, times r is 3/2h. That's being squared. We could do the derivative right here because we only have v's and h's, but it will be terrible because we'd have to do a product rule, a chain rule. It is much better to simplify first. And what can we do to simplify here? Well, we've got 3/2 h being squared. Let's go ahead and do that. 3/2 h times 3/2 h is going to be 9/4. This is 9/4 h squared times h. And this is still volume. We have not done a derivative. We've just simplified. This can be simplified more. I always try to get all of my constants together. This is a constant, this is a constant, this is a constant, and all of my variables together. H squared times h is h cubed. So what we've got is v equals, I'm going to multiply this out. This can be simplified, but I'll leave it unsimplified for now. 9/12 pi, this is all a constant, h cubed. That's v. I'm going to take the derivative with respect to t, so I get dv dt and dh dt. Let's see. So the derivative is going to be dv dt equals 9/12 pi. The derivative of h cubed, this is a constant. The constant multiple rule says you just leave the constant multiple times the derivative of this, which is 3h squared times dh dt by the chain rule. Okay. We can now substitute in. H is, let's see, when the pile is 15 feet high, so we're going to plug in 15. We know dv dt is 10. And so I'm going to go on to another sheet of paper here. So we get 10 equals 9/12 pi, 3 times 15 squared, dH dt. You can use a calculator on this problem. There's no problem to use a calculator on a bunch of these. Let's see, 9/12 is 3/4. 3/4 times 3 is 9/4 pi times 225 dH dt. And to solve for dH dt, we just divide. It's going to be 10 divided by 9/4 pi times 225. This can be simplified. I'm not going to do it here. You're welcome to use a calculator to find what this answer is. All right, the last homework that I'm going to do is we're going to do one problem like number 9 on homework. This is homework 2.6. This is a different type of problem. It says, a balloon rises at the rate of 8 feet per second from a point on the ground 60 feet from an observer. I'm going to start drawing right now because there's too much going on. There's a balloon. Hooray. That's a balloon probably. A balloon rises at a rate of 8 feet per second. This is a rate because of the per second. From a point on the ground, so there's a balloon rising above the ground, so we're going to probably have a height here, that is 60 feet from an observer. There's my observer. This is a balloon rising, and it's going up 8 feet per second. I'm going to go ahead and label this y. This distance will be y, the balloon's height, and so that makes this dy dt. It's how fast the balloon's height is changing every second and y is increasing. Find the rate of change of the angle of elevation when the balloon is 25 feet off the ground. Now, again, that's a value for y, but y is changing. So we're going to say like, oh yeah, 25 is what we're going to end up putting in for y, but y is changing. This 60 feet is staying constant. What's changing here is this angle. It asks for the rate of change of the angle of elevation. So it's looking for d theta dt. That's the rate it's looking for. So we need a relationship. Since we have d theta dt and dy dt, we need a relationship between theta and y. By the way, if you drew yours like this is completely fine. Like you have your balloon over here, your observer is here, it won't come out any different. Okay. Alright, so I need a relationship between theta and y. Theta and y and no other variables. So I really just want a relationship between theta, y, and this constant 60. Let's see. Theta, the relationship here that we can use is tangent. Tangent of theta is equal to the opposite over the adjacent, which is y over 60. And once we're here, we can just do the derivative with respect to time. d dt, the derivative of tangent is secant squared. So secant squared of theta times d theta dt by the chain rule equals, right here, y over 60 is the same as 1/60th times y. Dividing by a constant and multiplying by a constant are the same thing. It's just going to have that constant multiplier times dy dt. It's much easier to have the y in the numerator than y in the denominator. 60 over y would make us need to have 60 times y to the negative 1. This would be a power rule, and it would be a little bit harder to do than just taking the derivative of y. Okay, so let's see what we've got here. We need to find secant squared of theta, and we need to find, let's see, when y is 25, we need to do a Pythagorean theorem here to find what this guy is. So we're going to do, well, let's simplify secant first. Secant is 1 over cosine squared of theta times d theta dt equals dy dt was 8, so we've got 8 over 60. I'm going to go ahead and just solve for d theta dt here. D theta dt is, I can simplify this by dividing by 4. So dividing by 4 over 4, we get 2/15 times cosine squared theta. Now we need to know what cosine of theta is to find d theta dt. So to find cosine, cosine is the adjacent over the hypotenuse. We need to find the hypotenuse. So we need 25 squared plus 60 squared equals, I'm going to call the hypotenuse c squared. And so c equals the square root of, I don't know, 3600 plus 625, square root of 4225. I don't think that's an exact square root, but that is the square root of the, maybe it is an exact square root, maybe it's 35 squared. I don't know. I'm going to get a calculator real quick. I'm going to assume this is 35. I bet it is. I bet this is 35. So, 35 times 10 to the 6 joules per meter squared. So, 35 times 10 to the 6 joules per meter squared. So, 35 times 10 to the 6 joules per meter squared. So, 35 times 10 to the 6 joules per meter squared. So, 35 times 10 to the 6 joules per meter squared. So, 35 times 10 to the 6 joules per meter squared. So, 35 times 10 to the 6 joules per meter squared. So, 35 times 10 to the 6 joules per meter squared. So, 35 times 10 to the 6 joules per meter squared. So, 35 times 10 to the 6 joules per meter squared. So, 35 times 10 to the 6 joules per meter squared. So, 35 times 10 to the 6 joules per meter squared. So, 35 times 10 to the 6 joules per meter squared. So, 35 times 10 to the 6 joules per meter squared. So, 35 times 10 to the 6 joules per meter squared. So, 35 let's see, yeah, I'm going to assume this is 35. No, that's not right. I'm going to get a calculator real quick, guys. Hold on. Oh, I messed up something bad there. 3,600. Where the hell did I get this? 42. I was reading this as a 1225, which is why I said 35. Square root of 4225 is 65. My goodness, so bad. Okay, so the hypotenuse is 65, and so cosine is the adjacent over the hypotenuse. It's 60 over 65, and it's being squared. That's what d theta dt is. So we would just multiply this out. I don't know, it comes out to something. Let's see, 2/15 times, now that I have a calculator, 60 over 65 squared gives me 0.1136. In calculus, we round to 3 decimal places, and there are 2 ways we can round. We can round the next number correctly. 6 is above 5, so it would round to 0.114. Or another method of rounding that's acceptable on the Calculus AP exam is you can just concatenate, which means you just cut off the last digit after the third one. Either one of these is acceptable. Our units here would be radians, because we're measuring the angle. Radians per second, because the balloon was rising each second. So that's our answer. Hope that helps on your related rates.